Okay, so this theory video for the esterification experiment is going to cover how liquid-liquid extractions work. This is a key technique that you're being introduced to in this experiment, and actually it's a key purification method that's used for most organic reactions. So it's something that you really want to understand well. The better you understand what's going on with your liquid-liquid extraction for your experiment, the actual quicker you'll be, the more accurately you'll be able to perform it, so you get higher yields out at the end of your experiment. Also, if you encounter any problems, like you've forgotten what's in each layer, then in your conical flask, which ones contain your products, if you understand what you're doing, you can kind of overcome those problems quite easily. Okay, so this purification technique relates to concepts like the solvents and solubility. So we're going to recap some of the important details that have been covered in other theory videos. Firstly, you're going to be using an aqueous solvent and an organic solvent and placing it into a separating funnel. And because the solvents have different properties, your aqueous solvent can hydrogen bond very well, whereas your organic solvent will be non-polar and will only have weak van der Waals interactions. The two layers will separate, okay? And some of your one layer will contain your product, your key compound that you're trying to keep, and the other layer will contain the impurities that you're washing away and removing from your compound as well. Now, in terms of which layer is the top, the organic or the aqueous layer, it all comes down to which layer is more dense. The more dense solvent is on the bottom. So water has a density of 1. Okay, if you use an organic solvent that is non-chlorinated, then it will be in the top layer. So these will be solvents like diethyl ether or ethyl acetate. If you use solvents that have chlorine in them, so like dichloromethane, then the organic solvent will be in the bottom layer, because chlorinated solvents are more dense than water. And in those organic and aqueous solvents, you are going to be dissolving up things like your product, undesired starting materials, leftover reagents that you don't need anymore, or byproducts from the reactions. Okay, so thinking about what's going to dissolve in your organic and your aqueous layer, then okay, these are the solvents that you're going to be using. As I mentioned before, most liquid-liquid extractions use dichloromethane, ethyl acetate, diethyl ether as the sort of organic solvent. Okay, so what you tend to dissolve in the organic layer will be organic non-polarish sort of compounds. So things like your products or maybe your starting materials. Okay. In the aqueous layer, which is obviously really polar, you're going to dissolve things that dissolve well in water. So things that are ionic, so things like salts, for example, they will dissolve well in there. Or if you've got organic molecules but they're in their salt form, then they'll also dissolve in the aqueous layer, in water. So one of the things you can do is, if you can actually manipulate and change how well an organic compound dissolves in either an organic solvent or an aqueous solvent. And it all comes down to whether or not you have the organic molecule in the sort of neutral form, in which case it will dissolve in organic solvents, or if you can protonate or deprotonate the molecule to convert it into the salt form. If you've got the salt form of a molecule, then it's ionic, it's going to dissolve in water instead. Okay, so if we take a carboxylic acid, for example, and if we have an aqueous layer that instead of it being water, we have something that is a basic and alkaline aqueous layer, so something like maybe 2 molar sodium hydroxide. What the sodium hydroxide is going to do is it's going to deprotonate that hydrogen, it's going to take that away, and then convert the carboxylic acid into the carboxylate salt. So this salt is then going to dissolve in the aqueous layer rather than the organic layer. Same with a phenol as well. Phenols are quite acidic, so if you remove the proton, again with a basic aqueous layer, you create the phenolate salt, and then that prefers to dissolve in the aqueous layer. If you had an acidic solution or a water as the aqueous layer, well then these molecules would get protonated, be in the protonated state, so they dissolve in the organic layer instead. If we had an amine, well, what we can do in amines is these have basic functional groups. They can be protonated. So if we had an aqueous layer that was an acid, like 2 molar hydrochloric acid, then this will protonate the amine, and this will take this into the aqueous layer rather than the organic layer. And again, conversely, if we had an amine but our aqueous layer was basic, so sodium hydroxide, then the amine is going to exist as its neutral form, and it will stay in the organic layer. And so what we can do is we can manipulate this by, if we want to try and separate compounds, we can look at what functional groups that we can have. And if we can take certain compounds into the aqueous layer and remove it from other compounds that we can keep into the organic layer. And so this is exactly what we do in the esterification reaction. What you're doing in the esterification reaction is you're taking a carboxylic acid and you're turning it into an ester. Okay, but what you might have is you might have some leftover carboxylic acid. And so what the workup does, or the liquid-liquid extraction does, is it helps you remove any unreacted starter material. You have your organic layer, so which is ethyl acetate, and then what you do is you have a basic aqueous layer. So this is saturated sodium bicarbonate solution. And what that does is if you do have any carboxylic acid present, then it removes the proton of the carboxylic acid and it goes into the aqueous layer. Also, in the esterification reaction, you're using sulfuric acid to catalyze the reaction, which at the end of the reaction you want to kind of neutralize and remove as well. And what the sodium bicarbonate does is it reacts with acid to neutralize it to water, and also carbon dioxide gas. And so what you can do is you can remove the two reagents that you use, or the leftover starter material and the reagent you use from the reaction, into a separate aqueous layer. Then what you do is you open the tap of the separating funnel, and that bottom layer runs down into a conical flask. When you get to the line where you've drained away the aqueous layer, okay, and you've got to the organic layer, you close the tap, and then you change and swap to a new conical flask, okay, an empty conical flask, and then you drain away the organic layer. And through the liquid-liquid extraction, the organic layer will only contain your product as a crude material. You then just remove the solvent using a rotary evaporator, and that leaves you with a crude ester, where you've been able to separate out reagents and starter materials from the reaction. Okay, so that's a basic overview of how liquid-liquid extraction works. And most of the liquid-liquid extractions that you do in the lab will be undergoing these kinds of processes. And it all comes down to getting things to dissolve in the layer that they prefer, be it the organic layer or the aqueous layer. And importantly, we can also manipulate and change how compounds dissolve in organic and aqueous layers if we can protonate or deprotonate them as well.